All right, so now that we've been doing differentiation and finding derivatives by hand, we're going to look at the shortcuts. So these are the rules of differentiation. But to us, they'll be the shortcuts for differentiation. So, a few things to know before we start to go over the rules. First, all of these rules can be proved using the limit definition of a derivative. And if you don't know what I mean by that, I'm talking about the limit as h approaches 0 of the function evaluated at x plus h minus the function itself divided by h. So every single rule has a proof for it that comes from this definition. So now we're going to say don't use this anymore unless you are asked. Now in this case, from here on, we're going to be using these shortcuts instead of doing the longhand method, okay? So no more limit definition of derivative unless asked to do so. All right, so the first rule or shortcut is the constant function. And that says if we start off with a function where it's just like y equals or f of x equals a number, a constant, then the derivative of that is 0. So for example, if we had the equation y equals 3, then the derivative of that, or y prime of that, would be 0. The second rule we're going to look at is the power rule. And the power rule says that if you have a function that is x raised to some variable, then the derivative of that is going to be what you get if you take the exponent and drop it to the front, so n multiplied by x, and then you take your exponent and you subtract 1 from it. So, for example, if we had f of x equals x to the third power, then the derivative of that would be take the 3, move it to the front, so 3x, and then you take the exponent and you subtract 1 from it. So it'd be 3x squared. The next rule is the constant multiple rule. This rule says if you have some constant being multiplied by a derivative, some constant being multiplied by a function, and you want to take the derivative of that, then you're just going to say that's that constant multiplied by the derivative of whatever the function is. So whatever that derivative happens to be, you're just going to take it and multiply it by that constant. So for example, if we had y equals 4x to the 8th, and we want to find the derivative, I'm going to say y prime. I'm going to keep the 4 in the front, and then I'm just going to find the derivative of x to the 8th. And I know that that was you take the exponent, drop it to the front, and then take the exponent and subtract 1 from it. So 4 multiplied by 8x to the 7th, and we can go ahead and do the work to multiply that. That would be 32x to the 7th. In most cases, we are not going to show our work in between. We're just going to say, all right, 4 times 8 is 32, and then x to the 7th. That's what we'll do most of the time. The next rule is the sum and difference rule. The sum and difference rule says that if you have one function and you're adding or subtracting another function from that, and you want to find the derivative, it's just the derivative of the first function plus or minus, whichever you happen to be doing, the derivative of the second function. So for example, this one's going to take up a little bit more space. If we had, actually I guess I could have written it up there. Well, if we have f of x equals 7x squared plus 3x to the third minus 4, it's kind of like saying we have one function plus another function minus another function. So we can think of this all as like one piece, or we can say that these are three different functions that are being added or subtracted together. So to find the derivative, we're going to find the derivative of the first one. So I'm going to say 2 multiplied by 7 is 14, x to the 1 power, so I don't have to write the exponent, plus 3 times 3 is 9, x to the second power, and then the derivative of negative 4 is 0, and you can write it or not write it, it's up to you. All right, next we're going to look at the product rule. And the product rule says if you want to take one function that is being multiplied by another function and find the derivative of it, then you're going to take the first function and multiply it by the derivative of the second function. And you're going to add that to the second function multiplied by the derivative of the first function. And again, this is where I'm going to remind you that this rule that seems to not make sense and not come from anything, it actually comes from that limit definition of a derivative. There's a proof out there somewhere that explains why this works. And if you need me to, we can look that up and talk about it. So for example, on this one, let's say we have a function that is x to the 6th minus 1/8 x to the 4th, and that is being multiplied by x plus 2. So that means we're going to go back to this kind of formula here, the shortcut. We're going to say it's the first, so this is like your first function, this is your second function. So we're going to say it's the first being multiplied by the derivative of the second, so the first does not change at all. The derivative of this one, the derivative of x, if you have an exponent of 1, you would take the 1 and drop it to the front. So I give you 1. And then you have x, and you take the exponent and you subtract 1 from it, so that would be x to the 0. And anything to the 0 power is just 1. So this right here is saying 1 times 1. And so I'm just going to go ahead and erase that and say the derivative of x plus 2 is just 1. All right, so the derivative of just plain old x is 1. The derivative of 2x would have been 2. The derivative of negative 5x would have been negative 5. So anytime you have an x all by itself, you just take the coefficient. That's all you've got. And then we're going to add the second one, so x plus 2, times the derivative of the first one. So the derivative of x to the 6th would be 6x to the 5th. The derivative of 1/8 times x to the 4th, we would take these exponents and multiply them. So 4 multiplied by negative 1/8 would be negative 4/8, and that's the same as 1/2. X to the, drop it by 1, we get third. At this point, we got a little bit of work to do. This first one's being multiplied by 1. That's pretty simple. We can go ahead and just rewrite that. Over here, I need to FOIL this out. I got to multiply all that. So I've got x multiplied by 6x to the 5th, which would be 6x to the 6th. I have x being multiplied by negative 1/2 x to the 3rd, so that would just be negative 1/2 x to the 4th. Then I've got 2 being multiplied by 6x to the 5th. And I have 2 being multiplied by negative 1/2 x to the 3rd. Whew. So now, these are the derivative. I'm just showing my ridiculous amount of work here. So it looks like 6 is my highest exponent. So I have 1x to the 6th and 6 of them. So that makes 7x to the 6th. Then I only have one thing that has to the 5th. So I've got 12x to the 5th. And then with the 4th, I've got negative 1/8. And this was negative 4/8. So negative 1/8 and negative 4/8 makes negative 5/8. And then minus 1x to the 3rd, or minus x to the 3rd. You don't even really need the 1. All right, we have one last rule. I know that one probably made you not enjoy these so much. So the 6th rule is called the quotient rule. And so the quotient rule says, if you're taking one function and dividing it by another function and you want the derivative of that, then you take the derivative, or you take the bottom multiplied by the derivative of the top minus the top multiplied by the derivative of the bottom divided by the bottom squared. So yes, that seems like a really ridiculous problem. Now here, there's a little phrase my high school math teacher used to help us remember it, and she said low d high. So low is the bottom, d high is derivative of the top, minus high d low. So low d high minus high d low, and that kind of helped us to remember what the top should be, because that is kind of confusing, and the order matters. If you think about the product rule, if you got the order backwards, it wouldn't really matter, because you're adding these two things. You're just saying take one, multiply it by the derivative of the other, add it to the other, multiplied by the derivative of the first one, and you got it. Here, since this is a subtraction problem, we can't switch these. So low d high minus high d low kind of helps you remember that. Divided by the bottom squared. I don't know how that fits into the cutesy saying. Divided by low squared, d low, I don't know. There's probably some sort of trick for that one too. So here, our example, we're going to say is y equals x plus 2 over x plus 3. So it's kind of like saying our first function is x plus 2 and our second function is x plus 3, and we're dividing those. So we're going to say low d high. So the low is x plus 3. The derivative of the top is 1. Minus high d low. So the top is x plus 2. The derivative of the bottom is 1. Divided by the bottom squared. So x plus 3 squared. So then we just have to simplify the top a little bit. So I'm going to say x plus 3 times 1 is just x plus 3 minus x plus 2 times 1 is just x plus 2. And I'm going to put that in parentheses. And you're going to have to do this every single time, because this is going to happen every single time. It needs to be in parentheses because you have to make sure that you subtract each of the things. Right? So that's divided by x plus 3 squared. So now I've got x plus 3 minus x minus 2 divided by that same denominator. And the x's cancel. And so 3 minus 2 is 1 divided by x plus 3 squared. And goodness gracious, I'm finally done.